My name is Anita D'Amico, and Chris and I are affiliated with several organizations, and they're relevant to the talk that we're going to give on human factors and secure code development. So let me introduce the organizations. Applied Visions is a small business. It's been in business 30 years and develops business applications. And the reason that's relevant is that we're studying software engineering, and Applied Visions has a lot of software engineers, processes, and software, and we use some of those in our research. There's another organization, Secure Decisions, and it is a division of Applied Visions, and I run Secure Decisions. It's a cybersecurity R&D organization, and for the last 8 years, we've been focusing primarily on application security research. The reason that that's relevant is that the work, much of the work that we're going to talk about today was funded by the Department of Homeland Security through grants or contracts that were given to Secure Decisions. Secure Decisions, as a result of our research, publishes papers and articles. We produce open source software. In fact, this afternoon at 1:30, there will be 2 open source projects that we're presenting, one on Code Pulse and one on Attack Surface Detector, which were the outcomes of Secure Decisions research. The organization is CodeDX. CodeDX is an application security solution provider, and we take the results of selected work from Secure Decisions and we offer it to industry and government through a commercial entity called CodeDX. So that's it in a nutshell about our affiliations. By background, I am an experimental psychologist. I've been working in cybersecurity research for about 25 years, and what we're going to talk about today is actually the junction between psychology and application security. And I'm going to turn it over to Chris to introduce himself and the beginning of the presentation.
Thanks, Anita. So I started out working in policy research at the RAND Corporation and then moved into a career of human-computer interaction, software design, and ultimately product management. So it's in this role as a product manager that I help out at CodeDX. So I perform market research, understand customer needs, help shape the product roadmap. And the other hat I wear as a researcher at Secure Decisions. So there I help lead research projects that aim to further our understanding of cybersecurity and develop technologies that can improve application security. So like all great plays, this talk's going to be organized into 3 parts. Part 1, I'm going to tell you a little bit about the why we're looking at human factors and peek at the research that we've been doing. Part 2, which is going to be the bulk of the talk, we're going to go through a number of human factors that have been studied by ourselves and other academics. And in Part 3, we're going to open up the floor to a brief discussion about innovative ways that we could study human factors and learn more about them. This is Part 1. So the take-home from this message is that it's incredibly dangerous to have a red logo. There we go. Got my laugh. So it's not news to anyone in this room that it takes only one or a few vulnerabilities to give a malicious attacker an avenue to compromise or exploit a computer system. And this slide lists a couple here of situations in which a single vulnerability resulted in unauthorized disclosure of information for millions of people, right? And it's important to be able to quickly and reliably detect these vulnerabilities in our code. So this got us to thinking, what if we could identify source code that was more likely to contain vulnerabilities based on something about the developers and teams that wrote the code? So not technical measures, but measures about the people. That would be a new and different way to prioritize and focus our attention. For example, analysts and developers could choose to first triage static analysis findings or perform code reviews on code that was more likely to contain vulnerabilities. And development managers could use the same type of information to shape the work environment and foster more secure development practices. So today, we'd like to talk to you about the human factors that can influence software security.
So what are human factors? Human factors are properties of people. They could be psychological or they could be physiological. If they're psychological, then it could be at an individual level. For example, how well can you pay attention? How well do you learn? What have you learned? How do you make decisions? Or they could be group psychology properties, such as how groups collaborate with each other or how they make decisions jointly. There's also physiological properties of people that do affect their performance. For example, how easily are you fatigued? How well do you do with, how strong are you? And are you sick? Do you have a cold? The study of this, that there is a discipline called human factors psychology or human factors engineering. And what that is the study of how you account for these human factors when you design and engineer new products or processes or systems. Now, human factors is very well known in certain industries. So, for example, transportation. The FAA regularly publishes what they call the Dirty Dozen. These are the 12 human factors that are most likely to lead to accidents. The National Transportation and Safety Board, when they do an accident investigation, they're not just looking for mechanical failures, they're also looking for the human factors that contribute to the accident. And human factors are really the foundation that lies behind occupational safety. So Chris and I decided that we wanted to study how human factors affect secure code development. And we were particularly interested if we could identify human factors that affect code security, could we use that to prevent vulnerabilities in software? And also, could that be used to locate vulnerable code? And so we decided that we wanted to study the specific characteristics of developers, development teams, and their work conditions that might influence whether or not they are more or less likely to develop secure code. So we sought some research funding, and we went to DARPA. DARPA is the Department of Defense Advanced Research Projects Agency. It has a $3 billion a year budget, and they did fund all the research that invented the internet. It was called ARPANET in the beginning. And so we went to DARPA and we said we'd like to study this. And they gave us what's called a Small Business Innovation Research Grant, SBIR. They said, here's a small pot of money and 9 months. Go develop some methods and get some early findings and let's see what you got. So what you're going to hear today is the results of our early research as well as research that other people have done in human factors that affect secure code development. Now, DARPA was sufficiently impressed with the results that they are now going to fund us for another 2 years, starting in 2019. And if anybody here would like to collaborate on that research, we are looking for software development teams and software repositories to work with. So let's talk about what we did. We wanted to identify the human factors that affect code quality and code security. And specifically, we were interested in certain developer behaviors and characteristics, like their experience, training, how they edit files, how much attention affects their coding practices. We also wanted to look at team characteristics, such as the size of the team or how team members collaborate. And we were interested in the work conditions. For example, do human factors play a different role in open source development versus in proprietary code development? How do interruptions in the environment affect the way developers develop code? These are what, in research, we call the human factors predictors. These are the things that we wanted to study. And what we were looking for was the effect of that on code quality and security. That's called the outcome measures. And in order to look at the software security and quality, we chose 2 outcome measures. For open source software, we looked at publicly disclosed vulnerabilities. And for both open source and proprietary software, we looked at the type and number of weaknesses that were found when we ran the code through SAST tools. Now, the way we did this was called a retrospective analysis. It's basically a historical analysis. We picked a number of open source and proprietary repositories, and we mined data from them. We looked for human characteristics in the repositories. Now, in one case, we also had the developers' time cards. We mined data from that. And then we looked at the publicly disclosed vulnerabilities, and we ran SAST tools on the repositories, and we statistically analyzed the relationships. we looked at 4 repositories, at Chromium and Apache were the 2 open source repos. We looked at selected directories from them, and we looked at 2 proprietary projects. Now, some of these projects, notably Apache, have been around for a long time. And if it was around for a long time, we analyzed the entire longevity of the project, but we also really wanted to look at a smaller span of time, because there are certain factors like how many developers were on this project that just grow with the length of the project. And so we also analyzed the data in just 6-month snippets of time. So let me tell you a little bit about what we found. So one of the first things that we looked at was focused attention. And if a developer is kind of scattering their attention around different things, does that make a difference? And the answer is it does. In software engineering research, there is a concept called unfocused contribution. And it's an indicator of how much attention developers are focusing on specific files that they're developing. Now, unfocused contribution goes up, is high, when the developer of a file is also busy modifying a lot of other files. Unfocused contribution also goes up, or is high, when there are a lot more unique contributors to the file. So we looked at that and compared it to the security of the software. And in all 4 repositories, we found strong effects. The more unfocused contribution, the more insecure the code. And the more that developers had diffused their attention across files, the greater the likelihood of publicly disclosed vulnerabilities, the more SAST findings by specific types, and overall, the more aggregation, the cumulative number of weaknesses went up. This is just a picture of what one of them looks like. There's a statistical correlation there, and afterwards, if you'd like to know more about the statistics, I'd be happy to show you what this is about and how to read the graph. So in line with this idea of attention, we wanted to look at context switching. Developers tell us all the time about, oh, like I got interrupted, I had so many things, I kept on switching my time. So we wanted to look at whether multitasking or context switching had an impact on secure code development. And in one case, we had the developers' time cards. So we do a lot of work that's funded by the government, and we are required to account for our time in 15-minute increments. And people have to write down what they were charging, what billing code, and what they did. And so we looked at the number of distinct tasks or billing codes that developers charged in the time immediately preceding code commits. And since we were in the time cards, we also looked at the number of hours that they worked to see if excessive work would have an impact. And what we found was that there were more weaknesses in the code when, in the period immediately prior to committing the code, the developers distributed their time across a lot of different billing codes. Basically, they were context switching quite a bit. Also, there were more weaknesses in the code if they worked more hours. And this was true for the week prior to committing code, as well as the time between 2 code commits. So if any of you are looking for a reason to go back and tell your boss that you just can't take on another task, or you can't work long hours this week, here is your empirical evidence that says that if you do that, you're more likely to produce vulnerable code. So another thing we wanted to look at was inter-developer communication. And one way that developers communicate is through the comments. And we worked with Rochester Institute of Technology on this research, and they have the ability to do certain linguistic analyses of comments. And what we found was basically what I call the blather factor, which is the more verbose and less meatiness there is in the comments, the more likely that there are going to be vulnerabilities. And we only studied this in open source, so in open source code. I mean, it's basically, if you're full of hot air, files that have vulnerabilities are likely to have comments with them that have a lot of hot air with them. So let's just look at one of those. Before I show you this, let me set this up. So when we looked at these analyses, like let's say for Chromium and Apache, we looked at all the files and we dumped them into two piles. A pile of vulnerable files, that means files that had at least one publicly disclosed vulnerability. And then a pile of files that had no publicly disclosed vulnerability. We won't say they're not vulnerable, just that it hasn't been found. So we'll call them neutral. So you got a pile of vulnerable files and a pile of neutral files. And then what we wanted to see was, are there distinct differences between those two types of files? So take a look at this. This is Chromium, and the files with a vulnerability, the median number of words in the commit comments, the median, right, was 459, and in neutral files was 25. In Apache, the number of words, the median number of words in files with a vulnerability was almost 5,000, and in neutral files was 380. And when we did this and looked at this analysis more, what we found was that the content also was not as rich in these commit comments where they were very wordy. So if you want to talk about this later on, either stop by our CodeDX booth and we'll tell you more about how we did this analysis, or if we have time afterwards, I'll answer questions. So I was particularly interested in time of day, and I hypothesized that the time of day when code was committed would have an impact. So we took the day and we divided it into 6 4-hour increments, midnight to 4, 4 to 8, 8 to noon. And then we looked at the developer's local time zone, which we were able to do for 3 out of the 4 repositories. And we found absolutely no correlation between commit time and the number of weaknesses that were found by SAS tools. The teal is Chromium, the gray is a proprietary software, ChatSecure Android, and the orange is another proprietary project. This is markedly no difference. But we thought, well, maybe the time that code is committed does not reflect when it was written. So our partner, Rochester Institute of Technology, did another analysis on Chromium, where they looked at the code, and they said how much of this code was churned between midnight and 4, between 4 and 8 in the morning, between 8 and noon, et cetera. And what they found was that when the code was churned between midnight and 4, or between noon and 4 in the afternoon, or between 8 and midnight, that there were going to be far more that there were going to be more vulnerabilities. And I looked at that, and as a psychologist, I immediately saw what is called a circadian effect. Now, circadian rhythm is the way that your mental alertness and your physiological arousal changes cyclically over the course of a day. You ever have that 2 p.m. drop in attention? Well, that happens because of a circadian effect. And if you look at these numbers here, that it actually parallels the circadian rhythm. So I thought that was pretty interesting. We have more to say, and Chris is going to finish up. He's going to talk about environmental effects and also team characteristics that affect secure code development.
Thanks, Anita. So here on this slide, we have an environmental condition, which is the programming language that developers use to write their code, right? So the environment is kind of the language they're using. And the results are a little bit mixed. Some researchers find that certain programming languages encourage quality problems, and other researchers don't find that. But we're going to talk through these 2 bullets here where we have examples of where they did find an effect. So in the first bullet, one research team found that C++ code has lower error rates and maintenance efforts than C. And given over the recent years, there's been a decline in C popularity relative to C++. So it seems like other people might be agreeing with that. In the second bullet, another team looked at runtime failures across 7,000 software projects extracted from the Rosetta code repository. And what they found is, shown in this diagram here, that the compiled strongly typed languages like C# and Go had lower error rates than the dynamically interpreted languages like Python and Ruby on the left there. And other researchers haven't found these types of correlations, and it's generally kind of hard to study because it's difficult to tell whether problems are introduced by developer skill and experience or the programming language. So now we're going to look at team size. So this is one of the more robust effects that we're going to talk about. In general, larger teams seem to correlate with more vulnerabilities. So we observed in two of the open source, the Chromium and Apache, as we can see at the table at the bottom, files with a publicly disclosed vulnerability in their past had 7 to 15 times more contributors than a file without a vulnerability in its past. This was also true for the proprietary repositories that we analyzed, and there the files with more developers tended to have more static analysis findings. And in research conducted by our collaborator, Rochester Institute of Technology, looking at the Linux kernel, it turned out that files with changes from 9 or more developers were 16 times more likely to have a vulnerability than files with fewer authors. And finally, as we'll see in a couple slides, Microsoft conducted a study of post-release failures in Windows Vista binaries. And they found that only team size actually correlated with the post-release failure rate of the binaries that each team produced. And so this reminds us of a social psychological phenomenon known as the bystander effect. And this is where individuals are less likely to offer help to a victim when more people are present. So basically the idea is that everybody kind of thinks somebody else is going to take care of it, and so they don't kind of volunteer on their own. So churn, Anita mentioned churn. Churn is a less well-known metric about source code editing behavior. It's defined as the number of lines of code that have been added, modified, or removed in a commit in a source code management system, right? Like when people commit their code. And interactive churn is the amount of churn on lines of code that were last modified by another developer. So it's when people are editing each other's code. So if you had a file that had a single developer work on it, it would have 0 interactive churn. And again, looking at Chromium and Apache, we found that files with a vulnerability in their, I got to show that. So we're at the bottom here. Files with a vulnerability in their existence have 5 to 11 times more interactive churn than files never with a vulnerability in their history. And in that ChatSecure Android, which is one of the proprietary code bases, we saw that higher interactive churn was associated with more static analysis findings. So it also turns out that vulnerabilities can be correlated with what appears to be a lack of collaboration. So in this first item here, researchers studied a graph that describes how developers edit the same file. And they found that files that are worked on by multiple separate clusters of developers had a higher chance of containing a vulnerability. And so this analysis doesn't dig into the kind of interpersonal actions and interactions that developers are having out in the real world, but it is something that you can observe in a source code management system. So if you guys extracted this data from your systems, you could analyze that. And in the second example, the researcher found the 2 separate studies the same phenomena. So it's repeated for them. And the phenomena is that developers that edit mostly their own code tend to introduce vulnerabilities. So here the researchers actually figured that out by tracing back through the commit history to find the actual commit that contributed the vulnerability, and then they can attribute that to a developer. They call it a vulnerability contributing commit if you're Googling things. And so finally, that study I mentioned from Microsoft. So they were interested in the physical location of team members. And specifically, they kind of were interested to know if distributed teams produce software that has more post-release failures than co-located teams. And they actually looked at this multiple levels of co-location. They're Microsoft, right? They're huge. So they looked at whether the people shared, the team, 75% or more of the team members shared a common building, a cafeteria, a campus, a locality, or a continent, right? And what they found was that basically distributed teams and co-located teams had essentially the same number of post-release failures. So the location and the co-location of the team members did not predict in a meaningful way the number of failures. And in fact, when they kept digging, the only team dimension that they could find that reliably correlated with the post-release failure rate was the size of the teams. So this concludes part 2. And now we're going to jump into part 3, and Nita's going to give you that.
Right. Thanks, Chris. So if we were able to identify the human factors that identify code that's more likely to be vulnerable, then analysts that are triaging SAST findings would be able to focus on code that was written under work conditions or with human factors that were associated with more insecure code. Manual code reviewers would be able to focus on code that was written by developers or development teams that had the characteristics associated with writing more vulnerable code, or with the environmental conditions. And development managers would be able to change the work environment to be more conducive to secure code development. Now, I wanted to say something about the way we did the work thus far. So thus far, we've been doing work retrospectively, looking at existing code repositories. But there's there are many, probably most human factors that you can't measure that way. For example, how fatigued was the developer? Or how many interruptions did they have? Was it a very noisy environment? What was the team structure? And so what we are going to do next is what's called a concurrent analysis, where we look at developers as they code. And this will allow us to capture fatigue, team communications, the impact of a new training class on the developers. And we can do this with some very limited, lightweight instrumentation of the developer's environment that pops up and asks them questions like, in the morning, how many hours of sleep did you get? Or during the day, how tired are you? And we can even measure things like ambient noise in the room. Now, we already are going to do this starting in about 2 weeks in a proprietary environment, but we are interested in working with other teams and working with their developers. So if there is an organization here that we could work with, we'd really like to talk to you. And we're also very interested in whether or not we could do this for open source development as well. Could we find an open source team that would be willing to work with us in studying the human factors that go into open source development? So that's something that at the end we'd like to discuss. Also, I'm going to tell you about something else that we're planning. Rochester Institute of Technology and us are going to work on something called the Vulnerability History Project. And what it is to capture the life story of major vulnerabilities. And we will capture when the vulnerability was first introduced, how it persisted in the repository, what were the opportunities that were missed to find it, how was it eventually discovered, and how was it remediated. And we think that that will shed light on certain human factors that maybe contributed to either the discovery or the lack of discovery of the vulnerability. We're also thinking about, and we kind of like to get some feedback on this, of what it would be like to do hackathons, a 3-day hackathon where we could manipulate certain conditions. For example, we could change the team size. Everybody's working on the same thing, but one is a 2-person team, a 4-person team, a 6-person team. Or we could change the incentive, incentivize certain teams based on the security of the code, others based on features. We could look at, some of them can stay up all night and work, and others of them, we cut them off and make sure that they get sleep. So thinking about whether it would be possible to do that and what kind of venues we would be able to do that. And another idea that we had was, we're asked about this quite a bit, is how does one influence software developers to write secure code? And many people believe that security champions really make a difference. I don't know if that's been empirically measured. So it'd be interesting to have something like an open source project that didn't have a security champion, look at the security of it, and then introduce a security champion into the team, and then look over time to see if that made a difference and how that person influenced the rest of the team. So those are just some ideas, and we welcome your comments on that, and we'll open it up to discussion. And this is how to reach us, or you can go to the CodeDX booth afterwards, and we'll be there. Question?
Yep.
Yeah, good question. Have you happened to look at, because there's been this move in corporate environments from, individual offices to cubicles to mid-wall cubicles, low-wall cubicles, television from home. Is there any, have you looked at that and seen any correlation?
Okay, so the question is whether or not this move from, individual offices and cubicles to the big floor where everybody's next to each other, have we looked at whether or not that makes a difference? I don't know of any research that has done that, but it's something of interest to me. And based on other literature in other areas, we know that interruptions does make a difference in performance. And so where you are just easily distracted, that I would expect that it would have an impact on, in a bad way, on software development. So my sense, just based in other areas, is that those open floor plans may not be very suitable for the focusing attention. On the other hand, they can help with collaboration. So it depends on how they're set up.
And,
now, one of the things that people have done in response to that is put in earphones. And so one of the things that we're actually want to look at in the concurrent analysis is just to ask people during the course of the day, what are they listening to? Are they hearing conversation? Are they listening to music? Are they listening? What do they hear right now to see if noise distraction or music in the background, helps or hurts? Chris?
I got a couple more questions.
Okay, but
Yeah, are there any other? Yeah, here's the question.
Yeah, so if you go back to your previous slide, you talked about what you're planning to do going forward.
Yeah.
And I was curious about the concurrent analysis. Are you concerned that you have pop-ups coming up that could actually interact with the
Yeah, so there's a general.
can you repeat the question?
Oh, yeah. The question is that, we're going to have to be presenting pop-ups to developers to ask them about different things throughout the day, right? And so that is an interruption in and of itself. So it's generally a problem that, like, when you try to measure a system, you perturb it a little bit, right? So what we've tried to do is balance the interruptions. So we only ask twice a day, and we divide the day into 2 periods, and then we kind of randomly sample in those periods, and it varies. So basically, we're taking a sampling approach, and it's not predictable when that's going to happen. So yeah, basically the answer is we know that it's going to interrupt developers, and we've tried to minimize that, and we're using a sampling approach.
So there's a trend towards the DevOps culture, engineers being actually more responsible all the way through to production for what they're building. I was wondering if you considered this as well as a factor in terms of performance. Engineers feel more empowered to own what they're building and get more involved in the whole process.
I'm going to repeat the question.
Yeah, so the question, I'm having a difficult time summarizing the question, but basically DevOps has developers that are more involved in being responsible end-to-end for the security of their systems.
So, yeah, there's more aspects of the actual product.
Okay, yeah, take it. You can take it.
Yeah. So really, I think what we're dealing with there is motivation, right? And what people are accountable for. So in that kind of environment, you're incentivizing people to be more accountable. And that's something that we can study. And a lot of what we study will depend on what types of software development teams we have access to. So we're being fairly opportunistic about it. So if we have teams that are accountable, then we will compare them to teams that are not incentivized by that. Or perhaps even the same team, if they've done a shift over time, and we can study that shift from when they weren't in that environment and then the team takes on those roles. One of the values of this concurrent analysis is to be able to see the impact of an intervention like that. Yeah, we have 4 questions.
Yeah, okay. Let somebody else go.
So that's some very exciting results that you're showing here. I was wondering if you also looked at potential biases in the ground truth, specifically used the number of files that have vulnerabilities compared to ones that have no vulnerabilities. Potentially these files are also very large, like they contain the majority of code. Do you look at potential biases on that in your study when it comes to that, and what could be alternative ground truth there?
Yeah, so the question is there bias implicit in the use of files as your level of granularity for measuring problems, right? And so a lot of the metrics that we showed actually do normalize for file size. So we look at a density measure, or the metric that is used looks at a density measure, but when some of the cases we showed, not everything is adjusted for file size. So that is a bias that can creep in. So I would say it's kind of split, right? It depends on the particular definition of the metric, and some of those metrics account and normalize for file size, and others don't. That's a good point. On the red shirt, thanks.
Yeah, so I see the word quality on the slide here associated with security, which is nice to see. It's often easier to sell to managers the idea that they're improving quality rather than just security. So do you notice any quality impacts of the sorts of behaviors and environments that have impacted security?
Do you want me to take it?
Oh. So the question is, have we noticed whether or not there are quality issues that have impacted, or is there a correlation? Is that what you're asking?
Yeah.
Okay. All right. So when we did the analysis, we did measure. We used static tools, and they found both quality and security issues. And we have the data about what types. And we've done some initial analysis, but we haven't done, and we just haven't done it yet, the analysis of is quality and security related. I could tell you that in one of the cases for a proprietary project where we had access to the project engineer, we took all of the findings that we found, and we had him tell us, of all those things there, what was most important to him as a manager. And then we only analyze those, because there's a lot of stuff from static analysis that people don't care about. And so in one of the cases, he said, these are the 28 things I'm most interested in. And some of them were quality measures, and some of them were security. And we analyzed those 28, and in some cases, we would find significance in like 20 out of the 28. But we haven't gone down and done that next level of analysis. We could.
5. Okay. Here.
Have you used any of your analysis to identify potential vulnerabilities that have not been found yet?
Not yet.
Not yet.
But that would be the goal. Right? And I think we have to do a lot more analysis. I mean, we only analyzed 4 repositories. Each one was a different language. Now, there's some findings that we had that were quite robust, like team size, but I think further work has to be done to find what is that cutoff point in team size.
And I would just add, right now what we're trying to do is figure out what are those measures or metrics that are predictive of vulnerabilities or quality issues, right? So we're not yet trying to predict, we're just trying to learn what are those features that we can pay attention to. Isn't that great?
I was going to ask, is there a reason why you guys start off with security vulnerabilities specifically, just about in general?
Yeah, we were interested in security. and our funding source,
our
was interested in security. And they said quality and security, but when we actually went to them, when we finally got the funding, and we said, look, we can look at quality, we can look at bugs, we can look at security. We kind of are interested in security weaknesses and quality, the way that it's related to it, and we have to scope down. And he said, no, I'm really interested in the security. So that money talks, right?
Is the funder a static analysis tool?
No.
No, the funder is
No,
DARPA.
the DARPA, federal government.
No. And they don't have a dog in the fight.
Thanks for the presentation. It's really interesting to see something like this. Tom, one point of feedback on the lather slide. An example would have helped me better, but can you elaborate more on, I mean, it seems counterintuitive, the idea that code that's not commented, you've always kind of been taught that that's bad.
Commit comments. So we're specifically talking about the log message associated with like a git commit, for example. And if you just, I don't want to belabor this too long because there's quite a bit to the analysis. But basically, if you imagine somebody kind of writing lots of fluffy stuff that's kind of not necessarily on topic and using lots of words to describe simple ideas, that might, it's just a lot of words but not a lot of meat to it, then that's kind of the intuition behind the metrics that we have.
If you give us your card, your contact information, we can give you a more specific answer and some examples. And there was a graduate student at RIT who did that analysis for us, and we have access to him, and we'll get that information.
You have another
All right,
question?
go ahead. You've been dying.
Are you aware of, or have you considered putting together, say, a white paper infographic on, hey, here are things you can do with your team, or structuring your team, or having work to improve the quality or security of your
Well, we would love to write, I think it's too soon for an infographic. We really need to do a lot more analysis. We have a limited amount of data, which is why we really need to code repositories and teams to work with. But ultimately, that would be the goal. And I'm not convinced that a single infographic would do it, because it may be specific to whether you're doing open source or proprietary, or what language you're working in. Human factors may actually be mediated, the impact may be mediated by other conditions.
Last question.
Yep, last question.
Oh, okay. You mentioned team size. Is there support for like optimal team sizes in there? Does it say, like 4 to 8?
So we didn't look at the exact team size yet. So what we have is a correlation, and it tells you that as teams get bigger, there tend to be more problems. But you'd have to do kind of a sensitivity analysis and run it for different actual quantitative team sizes and do that analysis in a different way than we did it. So we could do that, but no, I don't have anything that's evidence-backed other than my anecdotal experience.
I think we're getting the cane to get off the
Yeah.
stage. Thank you.
Thank you.